I'm Richard Marshall, and as more and more people are exposed to machine learning based systems, I think it's important that we can teach people how machine learning works without needing to have an advanced degree in statistics. I spent some time watching videos on YouTube that purport to explain machine learning, and they were either super technical with either very strong coding skills required, or more likely deep statistical knowledge to understand them. Or there was another category that kind of assumed that you knew what some of these blocks meant, or they didn't understand them themselves and kind of skipped over the detail. So I decided that I'd have an attempt at explaining this, and I want to be guaranteed math free, so I decided I was going to use tomatoes. More strictly speaking, I'm going to use a tomato sorting machine as a concrete example of how we can actually use machine learning to do something that humans currently do in a very manual, labor-intensive manner. So today people put the tomatoes onto sorting tables and the humans sort them out into baskets. I want to build a machine that will do that based on various criteria automatically. So the tomato is going to go along the conveyor belt and end up in the right box. So let's have a look at the criteria. The first one is going to be weight. Under 75 grams is a small tomato, 75 grams to 150 grams is a medium-sized tomato, and 150 grams and over is a large tomato. So we could imagine the human laying them out on a table so that we can see them side by side, and then we can group them according to their weight and size along this axis, and we can put scale against it. So we've got 75 grams, 150 grams in here. So we can group them quite accurately. Now, how could we do this with our conveyor belt? Well, we can add a weigh scale. That's the dark grey box there. And what can happen is a tomato comes along the conveyor belt, it lands on the weigh scale, it's weighed, a small piece of code tells the gate to open and turn on the conveyor belt that moves the tomato down into box A. Very simple stuff. So we can write the specification for this in plain language really easily. If the weight of the tomato is less than 75 grams, put the tomato in basket A. Otherwise, if the weight is less than 150 grams, put the tomato in basket B. Otherwise, put the tomato in basket C. Now, for techie people, we can write this really easily. We don't need machine learning. We don't need AI because we can write it in code that's going to look something like this. We call this pseudocode. It's not proper code. It's missing lots of bits, but it's clear enough to read. So we can say if the weight of the tomato is less than 75, select basket A. Else, if the weight of the tomato is under 150 grams, select basket B. Otherwise, select basket C. So, yeah, nice and easy. The next criterion is going to be ripeness. So a green tomato is unripe and a red tomato is ripe. So we can use the color, right? So what we could do is put a camera above the conveyor belt to measure the amount of red and green and use that to select the corresponding basket. So we could write a piece of code, takes a picture and determines the color of the tomato. And if the color of the tomato is red, put it in basket A. Otherwise, put it in basket B. But, unfortunately, ripeness is a range of colours. It's not as simple as that. It goes all the way from green to red, and it's kind of patchy in various patterns in the middle. So it's kind of difficult to assess. Really not so easy for standard code to do this. And if we look at some photographs of tomatoes as they ripen, we can see that that colour pattern really is quite complicated across the 6 stages that it's showing in this diagram here of a tomato ripening. So this is an opportunity for us to use machine learning. So what we're going to do is we're going to take a few hundred or a few thousand photographs, the more the merrier, of tomatoes, and then we're going to get humans to go and label those pictures as to whether they are unripe or ripe, ripe, unripe, ripe, unripe, unripe. So we now have a set of data, a corpus that gets called, of labeled pictures. Now remember the fact that we're not just talking about the pictures, we're talking about the labels. So what we need to do now is to put them onto an axis in the same way that we did with the weight. Remember the arrow up the side of the weights that allowed us to group them into the different categories. So we can start off with an axis of redness. How red is it? This lovely ripe tomato is right up the top there. It's right at the top of the axis. We can also have a green axis. And the unripe one is at the far end of it. It's got no red in it whatsoever. It's fully green, so it's at the bottom on the right. We can then take the other pictures of the tomatoes and we can take photographs of those, and we can measure the red and the green across them, and we can put them across this surface using these dimensions of redness and greenness. Now we can use this to see that we've got two groups. We've got the group of ripe tomatoes at the top left, and we've got a group of unripe tomatoes at the bottom right. That's because we've laid them out that way against these axes. So what we can now do is use a piece of code that someone else has written. We don't have to understand how it works, but somebody who has a deep knowledge of statistics has written a piece of code that will allow us to draw a line through the middle of this diagram. And this uses some really well-established statistical technologies that have been around for forever. They're complex formulae. We don't need to worry about how they work. It's well known, it's reliable. What we've done is we've successfully labeled our tomatoes and put them into a space that enables that standard piece of code that someone else wrote to draw this line. And what do we use this line for? Well, we can start taking more pictures of the tomatoes as they come along our conveyor belt. So when the picture comes in, it gets put onto the chart, and whether it's below the line or above the line enables us to label the tomato. So we've used the fact that we can measure red and green to associate that with the label of ripe or unripe, depending on where it falls into this space between red and greenness. So we can now put a piece of code into our conveyor belt system that isn't just looking at the color. It's going to look at the tag. So we've taken a photograph of the tomato, we've put it into our chart. Is it above the line? It's ripe. If it's below the line, it's unripe. So we can say if the tomato's tag is ripe, put it in basket A. If the tomato's tag is otherwise, in this case unripe, put it in basket B. Now, we've used machine learning libraries to do this, so it's actually a machine learning application, but it's as simple as that. We don't need to know how it works, but we can apply it here because it is based on a very simple tagging system. Now, we now have a machine that can successfully label tomatoes as ripe or unripe. What if we want to tell if they are misshapen as well? That's another common criterion that stores are looking for. So, what do? Well, we start with our red axis and our green axis, and we're now going to add another axis, which is whether it's shapeful or unshapen. So is it a perfect shape or is it a misshape? And this gives us not a surface, but a three-dimensional cube into which we can put our tomatoes. So we're going to start with our lovely bright red, perfectly shaped one, and it's top left in the cube at the back, because it's perfectly shaped, it's totally red, there's no green in it whatsoever, there's no misshape in it. Equally, we can take our perfectly shapen green unripe one, and it's at the back right there. So it's fully green, it's a perfect shape, so we can put it there. This is a really strange misshapen one, but it's bright red, so it goes here, and equally this is a rather bizarre looking misshapen green unripe tomato, and we can put some of the others into this space. So we can fill this space up, just like we put the weights along the line, and we've put the coloured pictures across the two axes of red and green. So exactly the same technique, it's just working in 3 dimensions rather than 2. Now, what we can do here is, instead of drawing a line through the space, we can put a surface through the space so that the red, perfectly shaped tomatoes fall behind that surface, and then we can tag them. It's just like the line. We're dividing up the space. If you think about how you sort the cutlery in your kitchen, you'll have a box that has a divider for forks, a divider for knives, a divider for spoons, etc. within that space. Works just like that. So what we're doing here is we're using that divider to split the box, and just like before, we can start labeling the items according to where they fall, whether they're behind or in front of that space. A little more complicated. And after 3 dimensions, it gets even more complicated for us humans to look at, but not the machines. The machines don't care about additional dimensions, they're just numbers to them. So we've already taken the 3 dimensions and we've used this to determine whether a tomato is ripe, whether it's misshapen or not, and to automatically label them so we can use a machine to put the tomatoes into the right boxes. So that's how machine learning works. Basically, you don't need to know the details any more than you need to know how the motor of your car works. So let's have a quick summary of what we've learned here. So we need to start off by identifying the labels that we need in order to sort or filter things. In this case, we were looking for ripe and unripe. Is it small, medium and large? Is it shapely or misshapen? For tomatoes, our things are tomatoes in the example. Next, we need to find a method of determining the label. So the weight we can use very easily, it's a set of scales. For the color, we can use a camera. For misshapen, we can also use a camera. Now we use a human to take a whole pile of photographs of those things and label them. Might not be photographs, it might be text, but for the purposes here, we're going to look at photographs. So we've taken a whole pile of photographs and labeled them, and the more photographs you put in, the better the accuracy is going to be. Then we can use code that someone else wrote, so we don't need to understand the math behind it, that will divide up the space so that we can do the labeling. And once we've labeled the things, we can then use that to do something else. And then comes a super important point. We have to check the results. We have to monitor that the system is continuously working as we intended. And that's why we need to understand machine learning, because it doesn't always work. And circumstances change, the model might not necessarily change. So I hope that helped you understand how machine learning works. Please leave some comments and let me know what you think.